Professor Sengupta, your mic is not on. It's mute.
Yeah. Now is it okay?
Yes. So, sir, I would like you to say a few words. I already introduced Professor Chakrabarti, so you can say a few words now.
So, Professor Chakravarti, let me call you Krishnendu or Krish. So, hope you are well.
Yes,
Sorry
thank you very
for
much.
making you wake up so early in the morning. So, uh, so let me thank on behalf of KS University for accepting the request for delivering a talk on microfluidics to the audience. They are all really to hear your talk. This afternoon, the talk by Mr. Hope, the figures out. So, the audience. So, Kolkata, you can
Yeah. Thank you, sir. Thank you, sir.
to those who
Okay.
doesn't know him. Yeah.
Okay, so with a very brief introduction, I'll very briefly introduce Professor Chakrabarti. He received his BTech degree from Indian Institute of Technology, Kharagpur in the year 1990, and MSc and PhD degree from University of Michigan, Ann Arbor in 1992 and 1995 respectively, all in computer science and engineering. He is a John Cook Distinguished Professor and Chair at Duke University, USA, where he has been since 1998. His current research focus is on testing and design for testability of integrated circuits, especially 3D SoC, microfluidic biochips, hardware security, neuromorphic computing. Professor Chakrabarti is the recipient of numerous awards, to name a few, which include the 1999 National Science Foundation Early Faculty Career Award, the 2001 Office of Naval Research Young Investigator Award, and over a dozen of Best Paper Awards at top conferences and many more. He was also awarded the Distinguished Alumnus Award by Indian Institute of Technology, Kharagpur in 2014. Uh, he is fellow of ACM, fellow of IEEE, fellow of AAS, and a Golden Core member of IEEE Computer Society. He also held various honorary positions at several universities like Technical University of Munich, Germany, Tsinghua University, Beijing, National Cheng Kung University, Taiwan, University of Tokyo, Japan, University of Bremen, Germany, and many more. Thank you very much, Professor, for agreeing for this talk. You can please start your talk now.
Thanks a lot, Komalika, for the introduction. Thank you, Professor Sengupta. I may call you Indranilda. I've known you for a very long time, from my days as an undergraduate student. So today, I will walk you through my experience in doing research in microbiology and biochemistry on a chip, even though I never learned about these things as an undergraduate student. And it basically shows that research is something that constantly evolves and you learn new things as you go along. I will talk about our research in the early days when we were coming up with ideas, writing papers, working with students, on to commercialization, companies being created, IP being generated, and what lies ahead. So I want all of you to close your eyes and imagine the future. When you work in a new technology domain, you have to imagine what is possible and dream. You can't dream with your eyes open. So close your eyes and you can open them at the end of the presentation. And it's a lot of fun, but it's also very difficult because we do not know what lies ahead. There are a lot of unknowns and things that are very hard to predict in research. So I want to acknowledge many people over the years. We have worked in this area for over 20 years. A lot of students, postdocs, collaborators among our faculty at other universities. And also our research lab where a lot of experimental work gets done, a startup company that was acquired by Lumina. I will mention that in this presentation, and sponsors over the years, including the National Institutes of Health, the National Science Foundation, the Department of Defense, the DARPA, the Army, and companies as well. So this is the outline for today. I believe I have 90 minutes. I will finish maybe around at 75 or 80 minutes, so we have time for some questions. I will talk about the technology, give you some motivation for this area, commercialization success stories, and then talk about computing. Many of you are from a computer science or computer engineering background, so you might be interested in the connection of all this to computing or computational intelligence. But then talk about the gap that still exists. We haven't been able to solve all the problems. There are still gaps between microfluidics and microbiology. And I will cover the reasons for that gap and what can we do to bridge the gap. Talk about two advances whose focus of our current research is to enable a technology called MEDA and real-time sensing. And then looking at also security, there's a lot of concern about these products being hacked or being tampered with. So we are looking at techniques whereby we can protect these things. So the goal is to enable complex benchtop biomolecular assays on very small chips. And these chips would be programmable and microfluidic. So these chips are not necessarily chips that go into a processor, into a laptop, into a cell phone, but rather they are used for processing liquids, DNA or proteins. So we want to enable realistic biochemistry on simple chips. The chips would be simple because they'll be used by non-engineers. They'll be used by nurses and doctors and lab techs, but the chemistry must be realistic. So we want to go from, let me see if I can grab a pointer here. Yeah. So this is what exists in a lab. A lot of people in white coats with instrumentation. We want to shrink everything down to a small chip. Now, of course, we don't actually shrink the people, but we want to incorporate their intelligence and their experience and knowledge into these chips. So there's been a paradigm shift in biochemistry. So we were doing a lot of test tubes and microwell plates, complex operations, milliliters of fluid volumes. We needed skilled people. They had to be trained, paid a lot of money, and very bulky equipment as shown here. So instead, we can put everything onto a chip. We call it lab on chip or a biochip, where we can work with small liquid volumes and automate the operation by writing programs, writing software, using electrical or other actuation mechanisms. So why do we do biochips? Well, they are small. So tiny means that we have smaller liquid volumes, and that will reduce the cost and time to complete the reactions. You know from basic chemistry that you learn in high school or first year of undergraduate college, that the kinetics runs faster if the volumes are smaller. And then automation, less chances of mistakes. Things are programmed, so less human intervention, and very high throughput. So we could run lots of tests in parallel, get very high throughput. As a result, we can process samples much faster. So what's a biochip? Many of you haven't heard of this term before, so I thought I would have a slide to explain to you what it is. So it is a miniature disposable instrument. Okay, it is miniature, small, and it also has to be thrown away. You can't use it multiple times because you're dealing with liquid volumes and samples and reagents. So you have to throw it away after one time use, maybe 2 times, but not a whole lot. It's not possible to wash them. And they do what is called HTS, high throughput screening. So we want to do screening at very high speed, doing lots of them in parallel. And what does it do? Essentially, everything you learned in high school, when you were doing chemistry in high school, you had test tubes, you had your Bunsen burners, you were filling up your test tube with a pipette. You know, your thumb used to hurt because you were pipetting. At least mine used to hurt. And then we would shake the test tubes for mixing liquids. We would look for change in color, try to observe smoke coming out or any smells. And then when we are done with, we throw it away. Basically, we do all those things now on a chip. It's a lot faster and a lot less expensive, a lot cheaper than before. And what are the types of biochip? So the older category, the more mature category, is called microarray. I call them passive biochips because these chips don't do much work. So the liquid handling is performed by the instrument. A lot of the sample preparation, the pre-concentration has to be done either by hand on the benchtop or on some other instrument. And you present the prepared sample and reagents to a substrate, which could be made of plastic or glass or silicon or PCB. And on that, the binding happens. Essentially, you have probes of DNA and protein, and the complementary base pairs will bind to each other. You can shine light, use a beam of laser to understand where the binding took place. Okay. In this presentation, and the more active research area is called Lab on Chip, or Micro Total Analysis System, MicroTAS, where a lot of the active functions are performed on the chip itself. So we can control the flow, we can do the separations, we can stop and start the flow, we can even have sensors to detect endpoints or intermediate reaction points on the chip itself. And the reason why this has become so important because of cost. So this is a chart from EPFL. This is a famous Swiss university in Lausanne. They're looking at the cost in their currencies, Swiss francs, per unit weight. Okay, so per 1 gram, what is the cost of different things? So there's cost of copper. Copper is cheap. Copper goes into our tubings, our piping at home, but also on interconnects in chips. Then you have silver, a little more expensive. Gold is more expensive, platinum, and then sapphire and diamond, very expensive, right? Now, if you compare these to the cost of antibodies and reagents that we use for reactions, they are a lot more expensive per unit gram, per unit weight. Ampicillin, kanamycin, very expensive antibodies, right? So this is the reason why we want to reduce the volume, because we can reduce the cost. If your wife or spouse or girlfriend asks you for a ring as a sign of your love for her, you can, instead of buying a ring of diamond, you can buy a ring of antibodies, because they cost more, right? They're more valuable. So next time, do not buy diamond, buy a ring of antibodies. Anyway, let us proceed. Let's look at motivation for microfluidics. In the old times, we had test tubes. At the time, I used to be in college, we had manual reaction with test tubes. It was not automated, nothing was integrated, and it was very bulky, no miniaturization. Now you can have robots. This is a big industry. You can buy these robot systems, you can program them, highly automated, integrated, but bulky, not cheap. Okay. With microfluidics, we can get the best of all worlds. We can make a chip which could be the size of a coin, and they are fully automated. So you get things done without human intervention. Everything is integrated, and they're also very small. And we're talking about different categories of microfluidics. The first category is called a continuous flow, where we have etched microchannels. So if you look at this picture on the left, we have these serpentine channels, and then multiplexing as shown here. So these have to be etched using a lithographic process. And then you have various mechanisms to pump the liquids. You can have micropumps, microvalves, electroosmosis, electrokinetics, different mechanisms. You can integrate sensors. The problem with this approach is that, number one, you can't make these pumps and valves very small because they tend to leak. They have reliability problems at small feature sizes. The other problem is that the voltages you need for electrokinetics, electroosmosis is very high, thousands of volts. Okay, that is also a problem for if you want to have these used in the field for portable applications. And then finally, the liquid flow is not reconfigurable. It flows only along the channels that you have etched. So in contrast, we have been working with a technology where we have an array of small electrodes. On the right side, you see this picture with small electrodes, which can be addressed electrically. You can turn them on and off. And the liquid is moved not as a continuous flow in channel, but as individual droplets. So this is like a packet, okay, a packetization that is happening. And that's the payload. The payload can include DNA or proteins or many other things. So by controlling the voltages on these electrodes, we can either hold droplets at specific locations, or we can make them move. We can manipulate them. We can do all kinds of things with those droplets. So this is a lot like the transition from analog to digital. On the left, you have the analog perspective. And here we have a bit. A droplet is like a bit of information. You can have multi-bits. And there's also a clock signal because we can use that to control the electrodes. Okay, so therefore we call it digital microfluidics. So why does it work? So the physics behind this is electrowetting. It's known from the 1870s. There was a paper in French in the 1870s, which if you read French, I would urge you to read that. It's a very well-written paper, which talks about the fact that when you reduce the droplet volumes to nanoliters, very small, more microliters or nanoliter volumes, the surface forces start to dominate the forces in the bulk. The bulk forces get weaker. And what happens now is that if you have a very small droplet that sits on an electrode and there's an insulator, plus there is a very thin hydrophobic layer that I've not shown here, because you have a hydrophobic surface, the droplet makes a large contact angle. You can see this spherical shape. If I now apply an electric field between the electrode and the droplet, essentially I'm imparting energy into the system. So the energy is conserved. And what it does is it modifies the interfacial tension, and the droplet wets the surface. The surface changes from hydrophobic to hydrophilic, and the contact angle changes as shown here. Now this is entirely reversible. So if I take away the voltage, the droplet would bounce back to its original shape. I'll show you a movie here of a droplet on the bench. You can see there's a surface of the droplet. Right now, there's no voltage being applied. So let me see if I can start this movie here. Okay, I may have to, something is wrong with my pointer. Okay, now. Okay, so you can see that it'll make a one-time movement, one pulse, and then I increase the frequency of the pulses and the droplet starts moving up and down. So just to give you a little bit more background on the physics of how this works, we're talking about three different surface energies: the gamma interfacial tension between the liquid and the and gas, or the medium, the air, and then solid and gas, solid and air, and solid and liquid. So the gamma Lg and the gamma Sg remain constant; they do not change. But when I apply the electric field, the interfacial tension between the solid and liquid changes. Okay. They have to maintain equilibrium because there's no net gain or loss of energy. And this is called the Lippmann-Young's equation, which basically says that the new contact angle, which is theta v, can be expressed as a function of the contact angle when there is no voltage applied, plus this term. And you can see that this is like the parallel plate capacitor. Right? You have the square of the voltage, you have the dielectric constants and the spacing. Okay, so essentially this is like a parallel plate capacitor which can hold some charge. Okay, so this is the physics. I will not go more into this. We don't have time to cover that in much detail here. But let me walk into the applications, why this is so interesting. So if you have an electrode, a continuous electrode and a droplet on it, it would be like this. But if I now break up this electrode into multiple discrete electrodes with a small gap in between, and then I have a top plate which I keep permanently grounded, then I can make the droplet move. So if I apply a voltage that is high in the middle and low on the two ends, so you can think of this as a 0, 1, 0, it would trap the droplet here. If I want to make this move to the right, I would apply this electrode would be high and these two would be low. Maybe you cannot see my my pointer, so let me use the arrow, or this one here, laser pointer. So I would make this high, low, low, so 0, 0, 1 would push this to the right. To move it to the left, I would apply a high voltage here, low, low, so that would mean this is a 1, 0, 0, and this would make it move to the left. I'm just going to show you a movie here of a droplet being transported to the left and the right. You can see that. Again, this is done electrically. There is no pump. This all by applying the right voltage on the electrode. A few important things to note. One is there could be evaporation because the volumes are so small that if you do this actuation in a medium of air, there could be evaporation. I have seen experiments where within a few minutes, the droplet disappeared. Poof, where's my droplet? I can't find it. Well, it evaporated. Too bad, right? The other problem is of cross-contamination. If you are transporting large molecules like DNA and protein on these surfaces, they would stick or adsorb, okay? It's called adsorption. And to prevent that, we use a film of oil, inert oil, that does not interfere, but it prevents evaporation and also contamination. You can think of this as a finite state machine. We're talking about ones and zeros. So the state of the system is basically the voltages on the electrodes. And every time a droplet moves, there's basically a state transition happening because the state of the electrodes will change. And this becomes more interesting when you have multiple droplets being transported at the same time. Let's look at this movie here from the top. This is a top view of the chip. And you can see the droplet is moving very fast to the east, north, west, and south. This is not simulation. This is not being made any faster through simulation. This is the actual speed we get. So very fast transportation of these droplets. And this is going to show you a video of split and merge. We have two droplets that are going to be merged. When you merge them, you will get a larger volume of 2x. We want to get back to the original volume, so we'll do a split, and we'll get back two droplets of volume 1x each. So they merge, and then they split. So you can think of this as an instruction set. So when we were building these systems in the early days, we were actually talking about a microfluidic instruction set, which would have a microarchitecture, and we talk about instructions like move, split, heat, merge, and so on. Now, the outside world is not small droplets. The outside world is large volume, right? So we have to think of the interface. Just as in microcontrollers, we talk about an A to D converter. We read in analog signals, and then we convert that to binary values. So we can do something similar here. The left video shows droplet formation. We have a reservoir that is filled up. And then we would inject droplets from this reservoir into the chip by controlling the voltages on this line of electrodes. So let me play this movie here. I can basically do a sequence of ones and zeros that creates the neck, and then I can break the neck. So we can do this with very high precision. The droplet volume variation is very, very small. We have done this billions of times now over the years. The second video shows a dance, choreographed dance. We have multiple droplets being transported simultaneously, and you will see that there's no collision, no accidental mixing, because we can write programs, we can write software, and we know exactly where these are going. So you can see here these droplets being transported in synchronization. Okay, so this opens up the possibility of doing pipelining or parallel processing. So I could do various diagnostic tests on the same patient in parallel. Right? I don't have to do them on multiple chips. I do them one by one. So this, of course, became very attractive. Many people found this to be very fascinating, and there were applications in many different areas of biology and biochemistry. So in DNA amplification, polymerase chain reaction, pyrosequencing, protein-based assays, immunoassays using magnetic beads, for example. MALDI MS was shown on these chips. And cell-based. So we had cell culture. We could feed cells, and we can multiply cells in chambers using microfluidics. Or we could even do cell lysis. We can use chaotropic salt and open up the cell wall, extract the nucleic acids. Electroporation, we could bombard the cells, and we could basically inject material inside the cell. So these were all great demonstrations of the possibility of this technology over the years. And then there was a startup company formed from Duke called Advanced Liquid Logic, which was making PCB-based chips. So these were PCBs, so not really that small in size. The pitch was about 1.5 micron. This is the spacing between the midpoints of two electrodes. The gap height was about 0.5 millimeters, 50 volt actuation voltage. We had about 1,000 electrodes. And basically, the chip looked like this. There were lanes for transportation. There were reservoirs on the edges for storage of samples and reagents. And there was an optical region for detection. The overall layout looked like this. To decrease the cost, not every electrode was fabricated. So we only used the ones that we needed. And then from the user perspective, it looked like this. There was an instrument which had the power supplies and all the programs that ran on it. And the cartridge, the chip was a small throwaway cartridge, that was placed right here. And the user could see everything on the screen. So this product was very well received. And at around 2012, 2013, there were two counties in the state of Illinois in the US which mandated that every newborn baby was to be tested using these chips. So during that period, the company had sales of 500 chips a day. Okay, and of course you don't make much money on cartridges because they are throwaway and cheap cartridges. But when you have such high volumes, you can make money, right? And then what happened is that this became very interesting to a large company, Lumina, which is the world's largest DNA sequencing company out of San Diego, California. They bought this company, bought ALL. And they basically were very interested in the sample preparation part. So at their senior VP at the time of acquisition said that in the next generation sequencing workflow, they will use this technology. And interestingly, the transition from the acquisition to a product happened very fast. In most cases, it takes a while. You have an acquisition, then it takes a few years for the product to actually come out, right? But ALL announced a product within a year, and this was called NeoPrep, an easy-to-use system for preparing various high-quality NGS libraries. Okay, I'm going to play you a movie, sort of me saying what they did. Let them say it. So this is a movie that was made by Lumina. You will see here there's actually a lab bench scientist who is, and she is doing everything herself manually, and she gets very tired. You can see her, rubbing her forehead, and then she looks up and sees light, and you see the music will change, and and then you will see everything else. So let me make my volume maximum so that you can hear this better. And let me play the video. So you can see that she's tired. Everything is done by hand. And now she looks up. Okay, she looks up, and then the music will change. Good. So I'll stop here with the video. So you can see that by using droplets, and there were many droplets, not just one or two, like there were tens and hundreds of droplets being managed, being controlled at the same time. Then there's a company called Genmark, which licensed all this stuff. So they have a product called the ePlex system, which is used for infectious disease testing. And the main benefit of their product is that they can get all this done in less than 2 minutes. Okay, very, very quick. So let me play a movie from them as well. Okay, I think I'm going to stop this movie here. And the third company that I want to showcase is called Babies, and they are looking more at newborns. So you will see something here as well in this video. Okay. All right. So you can see that we not only were able to do the research in the lab, come up with the ideas and write papers, but we were able to transition these to actual products, which is actually sorry, sorry about that. So yeah, so I think it gives us a lot of satisfaction that the research we do is actually being used in products. Now I want to go a little bit more in depth into some of the optimization methods that went into these chips that allows us to use them for doing these things, doing many things in parallel. And here I want to bring this up by talking about what do we would like to do. We'd like to automate the labor intensive task, not have people run these reactions or assays manually, decrease the burden on chip users. So when we have a bioassay, we understand from the end user, from the chemist, from the technician, what should be the assay that runs on these chips. We map it to a fabricated chip using automated tools. We look at the scheduling problems, find out the droplet flow pathways, the transportation routes, configure the fluidic modules in a dynamic manner. We also monitor the chip for failures. If there are defects, some things go wrong, we can remap the bioassays. And here we have a big role for the CAD tools. So we can decrease the time it takes to get these chips to work, automatic reconfiguration when there is a fault in the chip, remapping. In some sense, we are mirroring the capabilities of a compiler and operating system. So we basically have tools that can map the application automatically to the microfluidic operations that run on the chip. And we also have an operating system that can keep track of workload and changes in the condition, congestion, and so on. And therefore, we don't need any more remapping of assays by hand for each application. So this is a lot like what we have in a PC. So if you think about using your PC, your laptop, you are running different apps at the same time. You have a web browser open, you are doing Microsoft Word, you are emailing, you have an email client, you have Acrobat running. Essentially, this is all done by the OS, right? It can manage all these things. So we can do the same things now on our chips because we have layers of software that can allow multitasking, multiple diagnostic threads to run on the chip at the same time. So let's look at how this is made possible. So we start by looking at what is the target application. We talk to the chemist, the biochemist. And for example, let's say we have 4 different types of samples. We have plasma, serum, urine, saliva, S1 through S4. And we want to run 4 quantitative assays on these samples. We want to understand the concentration of glucose and lactate, pyruvate, glutamate. These are my 4 assays. I could do them one by one for each sample, but I want to interleave them. I want to do it in a way that I get very high throughput. So I basically create a flow where I first figure out the architecture. So this is called architecture level synthesis. I figure out what are the different fluidic operations, in which order will they run, which can be in parallel, which have to be in series. And then I do binding of these to functional resources, and then I look at the layout. So I come up with the macroscopic structure. I map it down to where the different modules are placed, where do we place our mixers, our storage, our detectors, what kind of pathways must the droplets take, and we get the full layout that way. Okay. So essentially, we're talking about several optimization problems. At the fluidic level, we have to first model the assay, and one of the ways of doing that is to have a graph model where the various nodes in the graphs are fluidic operations and edges indicate dependencies. So for example, O1 and O2 are executed first, and the outputs are used by O4. And then we talk about the scheduling. At what points in time are the different operations run? as shown here. And then we have the placement and routing. So we have to figure out where the modules get placed and what transportation pathways the droplets will take. Then we look at the actual biochip itself. So we're talking about the electrodes that are being activated, which electrodes are used at which points in time. And then the addressing, we have to have control pins and we have to route them. So we have to have the wiring that goes from the input pins to the various electrodes on the array. So all of this has been fully automated. So this is a look at the tool flow. So we have inputs, which consists of the graph model of the bioassay, a library of the microfluidic modules. So these can be characterized in the lab through experiments. For example, we have a mixer that is 2x2 that has 4 cells and takes some time to run. We know what the time is. And then the specs of how large must the array be. So it can be more than 20x20, for example. We will have 4 optical sites. There'll be 3 reservoirs. And we set a limit on the time it takes to finish the assay. Okay. And the output of this would be the binding. So we would map the operations in this graph model to various resources. We have to also figure out when these operations will run. This is the scheduling problem, and then where they are placed on the array. And an acceptable outcome would be that the array area 8x8 is less than 10x10, and the assay time, which is in this case 25 seconds, is under my maximum limit. Now, let's look at some of these problems step by step. So the placement problem is very interesting. So in some way, it is similar to placement of VLSI chips, where we are placing, say, multipliers or adders or microcontrollers on the chip. But it's not the same problem because we have reconfigurability. So we can turn a module on and off based on need. So therefore, this is a lot like packing a 3D bin. This is a 3D bin packing problem where the X and the Y axis are the locations on the array where the module is placed, and the Z axis is the time axis. It tells us when the module is instantiated or used. So therefore, 2 modules can share the same XY coordinates, XY locations, if they are not used at the same time. Now, the 3D bin packing problem is computationally very hard, as you know, so we can solve it in a more practical manner by having a series of 2D problems. If we know the scheduling and binding, then we know what the placement, what modules are to be placed in each time step, so we can make the problem easier to solve by mapping it to multiple problems of placement in 2D. Okay. Let's work out an example. So this is a protein dilution assay. So we don't want to work with very large concentrations because they are, very prone to contaminations. So instead, we want to do a dilution. We start with a sample of concentration C, and we want to get down to C by 128 using a binary algorithm, where we start with a droplet of protein, we add a droplet of H2O, water, and then we do a split. So now we get C by 2, we continue the process, we get C by 4, C by 8, and so on. So this is called the binary or exponential dilution process. This is a very tedious thing to do by hand. So we'll try to get this done on the chip. So we have here the representation of the assay, and we set some limits on the assay time. Let me grab the laser pointer here. 10 by 10 is the size of the array. Assay time should be under 400 seconds, and we have some constraints on how many optical sites, how many reservoirs, and so on. And when we run through the tool flow that I mentioned on the previous slides, you get a picture like this. This is a 3D bin, and every component inside this bin is a microfluidic module. It tells you where it's placed on the chip and when it's used. The assay time is under my 400 seconds limit, so that's good. And the array area is 9 by 9. And we can also optimally find out where to place the transparent cells for optical detection so that we can have minimum time for transportation. Okay. Now, if we have faults, if there are some fabrication defects or some things go wrong and we can test it and we can figure out where those faults are, we can still use the chip. We don't have to throw it away. So we can increase the yield by using software to bypass the faults. So if these are the faulty locations, what I could do is I could create these black towers, and I enforce the condition that no module can be placed on these locations. So I have a a different bin. I have remapped the assay, and the fluidic modules are in different locations now. The assay time has gone up a little bit, 6%, but I can still make use of this chip, right? So, and this is how you can improve the yield by using your mapping algorithms to bypass the faults. The next problem that I want to mention is transportation or droplet routing. The goal is to minimize the time it takes to transport the droplets. This is in some sense similar to VLSI routing, because in VLSI routing, we have interconnects and wires, and we want to minimize the wire length. In this application, the problem is a little bit different because we don't have any actual interconnects or wires. Okay, everything is programmable. So the electrodes can be used temporarily for transportation. Once the transportation gets done, you can use it for storage or for mixing and so on. Okay, so if you look at the VLSI routing problem between S and T, you have a wire. Okay, it's there all the time. In the case of microfluidics, you can use the electrodes at this moment for transportation, and once it's done, you can use it for doing something else. So this problem is a lot like routing of railway trains or trains on a track. So tracks can intersect. So you can have crossing of 2 tracks and 3 tracks. That is allowed. But you want to make sure that 2 trains don't show up at the same time at the intersection, right? So you must have mechanisms to ensure that only one of these trains can pass to the intersection. And we do the same thing here. We have very strict rules on how close the droplets can get, and we want to make sure that at any intersection, 2 droplets don't come at the same time. The next problem I want to mention is of the addressing. So I told you earlier that we can control every electrode independently, and I actually was not speaking the truth. In theory, you can, but in practice, you don't want to do that because then the number of pins becomes too large. If I have a 100 by 100 electrode array, I have 10 to the 4, 10,000 electrodes. I don't want to have 10,000 pins, because the I/O pad frame is very large, and if I want to have 10,000 pins, I will need 10,000 I/O pads, and the package will be very big. So I need to make sure that I have a way to control a very large number of electrodes with a small number of pins. Okay, so I can decrease the cost. Yet I don't want to give up any of my throughput. If I have a few pins, then I have to move only a few droplets at a time. And as a result, the throughput becomes very low. So the constraints are clear. I would like to get very low cost with a very small package, means small number of pins, but I also don't want to have to lose any of the parallelism or the very high throughput. So how do I do that? One way to do that is to use a method called cross-referencing. And this is an idea that comes from addressing of SRAMs and DRAMs, where you use rows and columns. So if you have an n cross m array, you do not use n cross m pins, but you use n rows and n columns. So you have n plus m pins. Okay, so you basically will have 2 addresses for each electrode. There'll be a row and there'll be a column. Okay. So this works well. We have manufactured these chips and they work very well. The problem is that there is something called electrode interference. So the throughput is impacted. You don't have full freedom in terms of which droplets you can move at the same time. And I will explain that next. So let's take a look at this array of 10 by 10. I have 10 rows and 10 columns. Okay. And I have droplets 1, 2, and 3 as shown here. And I'd like to move droplet 1 down one location and droplet 2 up, and the third droplet will stay where it is. Okay. And what you will find here is that when I try to move 1 and 2, I'll also unintentionally move the third droplet. So if you want to move droplet 1, I would have to turn on this column and also turn on this column for droplet 2. And I have to turn on the corresponding rows. So I'll turn on rows 4 and 8. When I do that, I have now my 2 destination cells. These were intended, but I also have a couple of unintentional destination cells. So when I move droplets 1 and 2, I move the third droplet as well, and that is a problem. So clearly in this example, I cannot move 1, 2, and 3 at the same time. So this becomes more interesting when you have, more droplets. Here we have 9 droplets as labeled 1 through 9. And their locations are also indicated with the arrows. So 1 needs to move to the right, 2 needs to move down, 3 needs to move up, and so on. Can I move all of them at the same time? Okay, and the answer is no, because there'll be conflicts. So one way to do that is to move them one by one. So I first move droplet 1, and then I move droplet 2, then I move droplet 3. So this will work, but it's very slow because the number of steps I need would be 9. This is very slow. So the question is, how many steps do I need? Okay, can I form groups of droplets so that I can move all the droplets inside a group at the same time? So to solve this problem, we will make an important observation. And the observation we make is that we look at the destination and rows of each droplet. Okay, if 2 droplets, okay, have a common row or destination, then they can be moved at the same time. Okay. So then the problem is that of finding the optimal grouping plan. Can I form the groups must be very large so I can move more droplets at the same time, and I want to minimize the number of groups. Okay, so this is the problem. And the way we solve that problem is to map this to a problem of graph theory. So I take the array as shown here with the indicated movements, and I build a graph model where every droplet becomes a node in the graph. And I draw an edge between 2 nodes if their corresponding destination or rows are the same. Okay, so if you look at 1 and 2, they have a common destination column. This is the third column, and therefore they have an edge between them. There is no edge between 1 and 5 because 1 is moving here and 5 is moving there. They have no common row or destination. Okay, so therefore there is no edge between them. So I construct this graph, and then I do a click partitioning on this graph. Okay, I try to form cliques in this graph, and when I do click partitioning, I want to form the minimum number of cliques. So that's why it's called the minimal click partitioning problem. And when I solve the problem, all the nodes which are inside a clique, they are the droplets that can be moved at the same time. Okay, so in this particular case, 1, 2, 3, 4 can be moved at the same time. 5 and 6 it can be moved at the same time, and 7, 8, 9 can be moved at the same time. So the number of steps I need here is 3 steps. Okay. Then there is another interesting observation I can utilize to optimize this problem, and this is based on the fact that the electrode states are not just 1s and 0s. They can also be an X, means I don't care. So if I think about a droplet being held on E3, and then I need to have a 1 on E3 and 0 on the 2 sides because I don't want to exert any force on this droplet. But E1, I don't care. It can be X, right? I don't really care what is the value. It can be 1, can be 0. So by mapping these X's to 1s and 0s, I can do a lot in minimizing how many pins I need to access the electrodes. So let's look at this example here where I have a droplet on E2, and the droplet is going to be moved like this. Okay, it's moved to the left, then down, then to the right and up, and so on. Okay, this is the transportation pattern that I'd like to follow. Okay, it's a counterclockwise motion on a loop. I can draw this table that basically shows the activation sequence over time. So this is the first cycle, next, and so on, right? So you can see that in this table, you have entries that are 1, 0, and X's. Okay. So the point now is that can I map these X's very carefully to 1s and 0s so I can make some columns identical. Each column is an electrode in the array. If 2 electrodes are identical, means that they have the same activation pattern, then I can have the same input pin control both these electrodes, right? So to solve this problem, again, I would map it to graph theory, and I would draw basically a graph where every column or every electrode is a node in the graph. So I have nodes labeled 1 through 8 corresponding to the 8 columns or electrodes. And then I would draw an edge between two nodes in the graph if those corresponding columns in the table are compatible. And what that means is that in any row, the values are not contradictory. So if you have 1 and 0 in the same row, then they are incompatible. So for example, 1 and 2 are incompatible because you have 0 and 1 here. Therefore, there's no edge between 1 and 2. Between 1 and 4, you have an edge because if you look at the different rows here, either they are the same specified binary values or they have a binary value and an x, and you can map the x to the other value. So we draw this graph, and then we do a partitioning on this graph. All the nodes in the same click are columns which could be made identical, and therefore we can have the same control pin that can be used to drive those electrodes. Okay, so and the number of clicks you form in this graph is how many pins you need. And it's called broadcast addressing since we are broadcasting the activation from a pin. Okay. All right, so let us move on. And now we come to some of the problems we are facing, right? So far you saw the fact that we had a technology that works. They were patented, they were startup companies, there were lots of papers, many PhD students, companies were bought by other companies, and then there are products out there. But we have reached a stage where we have to do more to advance this technology if you want to enlarge the space of products out there. And while I was understanding what is the problem, I found this picture, which I think is very enlightening. This is a picture which is now a few years old, but it talks about the number of papers that are being published in engineering journals and in biology journals and medicine journals, which have the keyword microfluidics in them. Okay. So of course, in engineering, there has been a very sharp jump. You see lots of papers that talk about microfluidics. But if you look at the similar trend for journals in biology or medicine or interdisciplinary journals, there is a growth, but it's not very steep. It's not growing as fast. And there is this gap which grows bigger. Right? So what it tells us is that we are building all these cool things. We are showing that microfluidics works. We have droplets that can dance, that can do all kinds of stuff, but they're not being used as much. And you want to know why is this the case, okay? And why is this gap there? And I call it a trust gap because the biologists are not able to trust this technology. And there are many reasons for that. One is that till now we haven't done enough to support quantitative analysis. Most of the outcomes are yes and no outcomes. We want to also know what is the quantitative output. We don't have enough sequencing in real time. We can only know what happens at the end of the chemistry, end of the reaction. There are a lot of problems about defects and fouling when you have contamination on the surface. And the last one is security, and there are a lot of concerns of these being hacked. Okay. So first look at BQA, biomolecular quantitative analysis. So if you look at the protocols that we have worked with so far, they follow a straight line path. So we start from step 1, then we go to step 2, we go to step 3, and then we end the reaction. That's it, right? In actual practice, you have loops. Nothing works perfectly the first time. If you talk to a biochemist, you would realize that you may have to do some steps multiple times. So here is a protocol for gene expression analysis where you start with culturing of the cells. You have the samples, you culture the cells, and then you go up and look at assessment. You look at if the samples are contaminated or uncontaminated. If there's any contamination, you have to go back and do this step once again, right? After this step is done, you go to cell lysis, step 3. Then you go to nucleic acid extraction or isolation, and then you assess the quality of the isolated nucleic acid okay? And again, here, if it's not good, you may have to go back and continue more of this step. And then you do the PCR, amplification, and so on. So we have to make sure that we have, in the way we are modeling these protocols, we allow for independent but multiple pathways of the samples. We provide support for quantification and uncertainty about the pathway itself, because it's very hard to know in advance what the pathway is going to be. Are we going to go take this loop once or twice? Which steps will be skipped? Which steps will be done multiple times? It's not easy to know that in advance. So we need to make sure that we have a way of modeling that. And then there is a problem of defects. So this is a video of a chip where you will see a bomb. This is I actually call this a chip with a bomb because there'll be an explosion on this chip. So we have two droplets here and we want to combine them. So you'll see here a movie. Let me set this up here. So the droplets are being moved towards each other, but then this one just explodes. It's not moving at all, and then they come together and there is more explosion. Okay, so yield is a problem, and these chips they actually fail a lot. So let me. So then, and then we look at what are the different causes of failures. The dielectric charging is a problem. So over time, the dielectric starts to trap some charge. So the effect is not irreversible. It becomes irreversible, and droplet actuation becomes less effective. And in fact, if you plot this curve of number of actuations versus the threshold voltage, up to a certain number of actuations, you got a pretty low and a flat curve. You got a low threshold voltage, and then it starts to increase gradually, and then it goes up very quickly. At this point, it's failed. It can't be used. Okay. And the dielectric breakdown can occur because of defects like sharp edges and particles, contamination, pinholes can be formed, which actually concentrate the electric field intensity, and so on. I want to mention to you a specific problem that we have seen a lot. This is called the residual charge problem, because quite often we find that the electrowetting effect becomes irreversible over time. So here we have a large droplet of volume 2x, which is on electrode number 2, and there is some charge trapped under electrode number 1. So when charge gets trapped, then the electrowetting force is not as strong. So if you now do a split of this droplet between 1 and 3, because the force from 1 is less than the force from 3, the droplet that appears on 1 is smaller in size. Ideally, it should have been equal. We should have had equal volumes on 1 and 3, but in this case, that's not the case. That's not true, right? So you get a smaller volume here and a larger volume there. Okay. So and this is also a problem. And then I want to highlight the problem of fouling or contamination. And this is a really big problem. We can use what is called a wash droplet, but the problem with the wash is that the wash droplet has to be very large in size, and it's not as fast as the payload. So I'm going to show you an animation here of how it might work. So basically, we have a droplet that is going to start from this electrode T1, and I'm sorry, from S1 and S2, and their destinations are T1 and T2. So let me go back and play again. So a droplet gets sent from S1 and it contaminates this pathway. So when this droplet goes over this electrode, it gets also contaminated, and that's a problem. Instead, you can use alternate pathways. I can read out droplet 2, and it takes a longer pathway. It doesn't get contaminated, but it's slower, right? It's not optimal. So what can we do? Well, we can have a droplet go from here first, and then we can have droplet 2 come and wait for a while. I have a wash droplet that comes and goes through the intersection and does a wash operation, and then I move droplet 2. But you can see that this is also not very good because it has to wait, right? So instead, I can interleave the wash and the functional droplets. I could send droplet 1 like this, and then I could send droplet 2 and the wash droplet at the same time. So by the time droplet 2 comes, the washing has been done. So there are all kinds of interesting problems you can solve here. These are computational problems in optimization. But still, there are two issues. One is you can never tell that the washing was successful unless you inspect. So how do you know that the wash droplet picked up the mess? Right? That's number one. Number two is that the wash droplet has to be large in size. It has to be a big droplet, and it's very slow. So the animation that I showed you had a wash droplet moving very quickly, but in practice, it moves, it's not as fast as this. It's very slow. Okay, so next I would talk about a platform that helps us to address these problems, and this is called MEDA, a microelectrode dot array, where the idea is to have lots of very tiny microelectrodes, which can be automatically configured to form larger electrodes. So you can have different shapes and sizes. You can have a 2x2, a 2x4, a 5x10, so different shapes and sizes, and they can be formed. This has been manufactured using TSMC, so it's a foundry process, so we have a very high yield. And also we can put sensors under every microelectrode. So under every microelectrode, you have a transistor-based sensor which can detect droplet presence, droplet volume, droplet type, and so on. Okay. So it also helps you to do movement of droplets in a diagonal fashion. So you can see here, instead of going just along X and Y, the droplet can move along the diagonal like this. And then we can manipulate the droplets of various sizes. It's not that we should have all the droplets the same size. We can have a small droplet and a large droplet, as shown here. Okay. So you can see that the large droplet is being moved to the left, and they merge. Okay, this works very well. Let's see, pause this and go to the next slide. Okay, so then I come to the last part of this presentation, which is looking at can we trust the outcomes? Okay, if you look at trustworthy execution of biomolecular quantitative analysis, we have multiple steps. The first step is to prepare the samples and reagents, right? So make sure that you get the right concentrations of sample and reagent. Step number two is what is called sample differentiation. You would use various beads or barcodes to carry out sample differentiation. And the third one is the actual protocol execution. Threats that we can have here can be at multiple steps. Okay, we can have a bioassay threat, which can lead to basically caused by a malicious attack on the platform itself. And for that, we have done work on encryption. So we can do microfluidic encryption so that we can make sure that the protocol is not attacked during execution. But there could also be attacks elsewhere. The attack that I will talk about right now has to do with a bad actor trying to tamper the sample and reagent. Okay, so this is what we call the biochemical level threat. And what I'm going to do now is give you a quick walkthrough of a benchtop experiment we did to understand what are the attacks somebody can make on the sample, on the DNA preparation itself, and also what countermeasure is there to offset that. Okay. So the objectives are the following. We want to study the adversarial execution of DNA preparation, the attack models. We want to assess the stealth of these attacks. Are these attacks easy to catch, or they remain concealed? And then we want to have a biochemical countermeasure to address the problem. So we did the following. We prepared 6 types of crude DNA samples. Okay, so this is how it looked on a petri dish. And then we got the PCR, which is the polymerase chain reaction. We got the master mix for the PCR. So the usual reagents of the PCR are the following. We have buffer, we have negative controls, we have primers and some salts and so on. Okay, and of course the enzyme that you see at the polymerase. And then we took various PCR strip tubes. We had, for example, the third tube was 1 microliter DNA sample, sample number 1. There were various DNA samples. We took this was sample number 1 plus the master mix, which is shown here. Or we could take tube number 4. Tube number 4 was sample 2. It had 1 microliter of DNA sample 2 plus the PCR master mix. So we did all those tubes. Okay, and then we have the NTC, negative control, where the DNA wasn't there, so there's no sample here. And then we had the PTC, or positive control as well. And then once we created all those tubes, we transferred these strips to a thermal cycler, which is shown here. And then we could do what is called gel electrophoresis. Okay, this is the final step, and this is the golden assay. So the golden assay is where we haven't done any tampering, and usually you see this kind of a tube in gel electrophoresis. You have a DNA ladder, you have the NTC, PTC, and then you have the various samples: sample 1, sample 2, sample 3, and so on. Okay. So the attack models now. So attack number 1 is that we call it PDOS, positive denial or service, and the attack surface is the PCR master mix. So the attacker is going to tamper with the PCR master mix, and it's going to basically add a small quantity of the the amplifier as shown here. Okay. The attack number 2 is also on the PCR master mix, but it is NDOS, or negative denial or service, and it's going to be adding some inhibitor, add a small quantity of NTC into the master mix tube. Okay. And the third attack is where we switch the samples. Okay, this is the more insidious attack. So we want to basically interchange some of the tubes. Okay, so DNA sample switch forgery attack, and we're actually extremely keen to see if we can catch this easily. Okay, the attack surface is the sample preparation or the PCR strip preparation, and the implementation could be that we can switch the DNA samples or add external samples, and there is no change which you need to do in your PCR master mix. So we, again, ran experiments here. So we loaded the DNA samples into the gel for the gel electrophoresis. We have 4 regions. So the golden assay is region 1, which is shown here on the top right corner. Region 2 is attack number 1. Attack number 2 is region 3. And the attack number 3, which is where we interchange the DNA samples, is the 4th region, region number 4. The DNA samples we know from our basic chemistry or physics, these are negatively charged molecules, so they migrate towards the positive electrode, as you can see here in this picture. And if there is no DNA amplicon process, that is, if you have negative control, then there is no more migrations. For example, here in S1. Okay. But you can also understand the amplicon size from the speed of migration. So basically, we can distinguish DNA based on size by looking at their migration rates. Okay. So now we look at the outcome we got from the various attacks. So this is the first region, the golden assay. This is how it should be. Okay. Region 2 is attack number 1, and you can see that we have some places where things have changed. So this we can catch. Okay, we can catch it by inspection. So by inspection, we can know that there has been some tampering, right? The third region is attack number 2, where because it is NTC, there is no amplification, and we can tell that this is also wrong. Okay, this is not correct, right? But pay attention to the 4th region. Region 4 and region 1 are very similar. Okay, and we have worked with our collaborators who are biochemists, and they have consistently told us that this is impossible to tell. So here we would actually pass this as acceptable. Okay, so therefore attack number 3 can be a stealthy attack, an attack which we cannot catch. Okay, and this is a problem because an attacker can forge the sample, and it's impossible to know that it has been forged. Okay, so the mechanism that we have to counteract is to use what's called a DNA barcode. So we have a sample, and then we add a barcode into the sample, and then when the collector transports the sample, the collector transports a sample with the barcode as well. Okay, and the analyzer is going to first check with a primer, which I will talk about soon, to check with the primer if there is a barcode match. If there's a barcode mismatch, then the sample is not trustworthy. It'll be thrown away. On the other hand, if the barcode matches, then the analyzer would do the actual quantitative analysis. Okay. To implement this, we basically are going to first look at what is the benefit of this, right? So a DNA barcode is a unique sequence of nucleotides, and the order of these forms the barcode identity. Okay, so we have these 4 nucleotides, right? G, A, T, C, and the order in which we place them is going to be the barcode. So if a barcode is of length L, then the number of possible structures we can have is this. It's exponential in L, right? So this is a very large number. So for example, if L is 280 base pairs, if we have a barcode of 280 base pairs, which is not very, very long actually, the number of possible structures is very, very high. You can see this number here. Okay? Now, each barcode will require 2 specific primers for amplification. There's a forward primer and there's a reverse primer. So this goes in this side, this goes on the other side. So for a primer of length P, okay, the number of possible primer structures is again exponential in P. So clearly, if we have a primer which is 21 base pairs, we're talking about a very large number of possible primers. So if somebody wants to just guess, the success probability is very small. Okay. So in some sense, if you think about what we are doing, adding a barcode to a sample is like adding a door lock. So we have a door, which is our sample. We are now onto the door, we're adding a lock, okay? And only an authorized person with the right key can unlock the door, right? So the right key here is the barcode specific primer, okay? And the primers are included in the master mix. So if you don't have the right primer, you cannot unlock it, okay? So now let's see how all this works. So we have a trusted party, some central authority that would maintain a database which is secure. So that would have these 3 fields. There would be a secret ID, let's say all X's, and then this is the first barcode, a barcode 1, and then the primers for this barcode 1, bar 1F and bar 1R, the 2 primers we need. And for barcode 2, we have a secret ID of YYYY, and then the barcode primers are bar 2F and bar 2R, right, the 2 primers. So what we do is that the collector is going to be sent only part of this information, not the entire information, right? So there would be an encryption process in an encrypted manner. The collector is sent the information of the secret ID and the barcode information, and the analyzer would be sent the secret ID and the primer information, okay? So the collector would do the barcoding, making use of this code. It does the barcoding chemistry using the biochip, and then sends the barcoded DNA sample into the analyzer. And then there is an electronic channel. In a separate encrypted electronic channel would send the encrypted sample and barcode IDs. So this XXX's information would be sent along the encrypted channel. The analyzer would decrypt this information and would first check using the primer if the barcode matches. If the barcode matches, then the sample can be trusted. If not, it's not trusted. Okay, and that's how it would work. So we did this on a benchtop to show that this really works. So let's say we have 2 samples, S1, S2. Let's say we have barcode 1, barcode 2 with 280 base pairs and 190 base pairs. We basically use barcode 1 with barcode 1 primer, then we use barcode 2 with barcode 2 primer, and we use the combinations of the 2. So we want to also see what happens if we use barcode 2 and the primer for barcode 1, okay, and so on. And then all the primers. So you can see here, I'm running out of time, so I'll be very quick. So basically what we were able to show is that, when we have negative control, barcodes are not amplified, whereas if you're using the actual primers, and we get amplification. And here, because we are using the incorrect primers, there's really no amplification. So the forgery attack can be caught in this case. So let's analyze this mathematically. What does it bias, right? So to successfully forge a biosample, we need to also forge the barcode. So if you have a naive attacker who doesn't know the biology, would just randomly guess. And here are some probabilistic analysis. If S is the event that we can guess the right nucleotide order, and L sub P is that we guess the right primer length. So then we can write this as a conditional probability. And basically, the probability that we can forge a barcode with the same primer design is very, very small. It's 1 by 2 to the power of 90, virtually impossible to do that. On the other hand, if an attacker is an expert who knows some biology, the attacker would infer that maybe a plasmid was used to build the barcode. Okay, now plasmids are smaller DNA molecules. So the attacker would use some more information to guess the barcode, would guess the right plasmid and guess the barcode length based on the right plasmid, and then it would guess the segment from the plasmid vector. So then you can, so you can actually you can calculate this probability, which is also actually very, very small. So even if you have knowledge about the biology, you know that this is a plasmid and you can guess the right plasmid, the probability of doing that is 10 to the power minus 11. So it's still very, very small. Okay. And you can draw some nice plots like this, which basically says for different widely used plasmid vectors, these are some of the common plasmid vectors, what is the probability the attacker can find the barcode that uses a specified plasmid. If you increase the barcode length, you can see that the probability becomes very, very, very small. Okay. Okay, so that brings me to the end of this presentation. Basically, what I tried to walk you through was that digital microfluidics offers a very attractive platform for doing lab on chip. The main applications now are diagnostics and biomolecular recognition. There have been lots of success stories in commercialization in the recent years, but the applications have been more in sample prep, immunoassays, and clinical diagnostics. But there are other applications that have not yet been touched. Right? Further growth is stymied right now by technology limitations. We have to identify fixes to these problems of defects, fouling of the surfaces, can we have quantitative analysis and trust. Okay, and the promising paths forward that I'm looking at are MEDA and barcoding. So finally, we now have this kind of a biochip ecosystem. So on one side, we have those who are building the chips, the engineers who are doing the chip design, layout, manufacture. And then we have the users who are making use of the chips. And in between, we have the computational intelligence. We have all the software, all the tools that allow us to map the various interesting applications onto these chips. Thank you. With that, I end my talk.
Thank you very much, sir, for taking us through this microfluidic journey, where you introduced about the topic, then told about different techniques, and also posed some threats and challenges that are existing, which could be taken up in future. Now, I would like to ask the participants to ask questions if they have.
Yeah, thank you, sir, for the talk. I would like just to ask the question on operation variability, sir. You have talked whether we can use any evolutionary technique, any AI or ML technique can be used, sir, to route the path for the wash droplet that you have discussed.
Okay, if you can, I think there's some. I can hear you well.
Can you hear me now, sir?
Yes.
Oh, yes, sir. So I was just wondering, you have given a talk on that operation variability, sir. So there you have talked about the part regarding the wash droplet, the part. So any mitigation techniques such as AI or ML can be applied there? AI or ML techniques?
Okay, yes, sure. So there's actually a lot of ongoing work now on trying to use machine learning for adaptation. What is not clear is design your chips. The environment is not known. What is that? There's some background noise here.
Yes, I will read out the question. There is a question from Shushmita Shurkole, madam. So she is asking, she's saying, hello, Krishnendu, excellent talk. Will biochips add to e-waste even more? Would disposal have potential of spreading infections?
Okay, yeah. So excellent question, and hello to Shmita Di. Yes, e-waste is a big issue, especially as we increase the volume of sales. So right now the volume is small. These are used more in the labs for research. The chips themselves are very small, and they are, if you think about what is in those chips, it's very easy to decompose them, right? So it's not that you would have these chips staying active for too long. But when the volume goes up, when you have every hospital or every clinic using such chips, there has to be a process for destroying them. Okay, and that has not been worked out yet. So it's not yet clear if we have very large volume, what is the mechanism that has to be used to destroy the chips. So e-waste is an issue. There's also the concern of counterfeit. So if a chip has been used already and it's not been discarded in the right way, the rogue user make use of it. Process whereby we can destroy chips which have been used. I think going back to the first question, which I didn't hear that well, it's about using AI, right, for my microfluidics. So I think that's a very good question. Right now, when you design the chips, we do not know what environment those chips will be in. So the operational mode is unknown, right? We've seen some things about the temperature, the humidity, vibration, and we will do the optimization with. But we have some ongoing work elsewhere too, where we are using various machine adaptation on the fly. It's not for the washing, because personally I don't think it's going to work. It's very hard to make sure these chips can be washed. But it's more to address degradation field. When a protocol gets mapped to the chip, certain electrodes get used more often than others. Those will start. When that occurs, is there a way to, remap your assay? Do that in advance, not actually wait for the failure to happen. For the electrode to fail, you may get in assay outcomes. But if you can sense online, you might be able to predict that this electrode will fail, and hence take action early.
Any other questions?
I have a general question. May I? So Krishnendu, what I was asking is that suppose some of our colleagues from our university gets interested to pursue research in microfluidics. But to understand that here we lack access to actually experimental setups, like where you can actually do the experiments like what you are doing, your research group is doing. So what do you suggest? What kind of research they can focus on? And secondly, if they want to collaborate with your research group, what are the possibilities?
Okay, so collaboration with experimentalists is the key. If you want to work in microfluidics, you have to show that any algorithms you are coming up with actually work in practice. So it's very hard to work in isolation alone.
Yes,
So
absolutely.
if you can find a partner in your university who is a biologist or who does NAND, who can manufacture or do some small scale fabrication, that would be ideal. But it's also fairly easy to do your own manufacturing, PCBs, for example, or soft lithography, because there you don't need a fab. So I'm not a I'm not somebody who works in the fab. That's not my research. But I'm making PCBs in India. For that, it's very easy. So you can use standard tools to design the PCB. Basically, you can say this is what I'm going to put some electrodes. I will put some interconnects here, and you can fabricate them very cheap, very easily. So our PCB is very Lumina, which we use right here. It's very close to and we can get the fab structure. And once we get the PCB structure, we can start manufacturing.
Okay.
Applications is it's not impossible to do some very basic fabrication when you're in the lab. But of course, ideally, you must have a partner who is from the application side, right? Who's not just a
Right,
fab
right,
person, who is a biologist, and I'm not a biologist, so
right, right, right.
collaborating with
Understand.
me, you are more than welcome to partner with me. I'm always looking for good collaborators.
So,
But
we also have a
I
department of pharmacy. We have a department of pharmacy.
that would be
We
great
can
if you
get the
can
get the expertise
present
from
some
there.
of this to
Yes.
the pharmacy people and tell them
Right.
that what are your applications, what problems are you looking at.
Right.
That is ideal, because otherwise it's like you have something that is solving an unknown problem, right? You don't have a problem to solve first, so it's best to work
Right.
on the
Right.
problem
Absolutely.
and then find a way to solve the problem. Yeah, so at Duke we are very fortunate. We have a very big medical school. We have engineering. I work with people there, and that is very insightful.
So much.
Okay. Any other question? Any other questions? Okay, if there is no other questions, then I would like to ask one question. Like, see, there are so many pathological tests that is generally conducted. So, if that is so, when you talked about the architectural design, so will that architectural design be robust for the entire set of chip you design? Because you have to build different kinds of chips, right? So,
Kamalika, I think this is a very nice question. So ideally, we want to have a general purpose chip that can conduct all these tests. You want to have a platform that is powerful enough so that it can be programmed, and you just change the program for various kinds of tests. You want to test for COVID, you run program number one, and then you want to do a test for hematology, you run program number two. That is the longer term goal. We'd like to be there at some point, but right now these chips that you saw in practice at these companies are that specific application. So these are not really so powerful. The main issue being that the customers are from that area only. So if I'm a customer who only wants chips for COVID, I don't care about doing any other tests. I'm just going to buy low cost chips that can do. There are also issues about the accuracy that different kinds of tests need. So if you want to do test one, test two, and test three, they may have very different needs in terms of the accuracy. So on the same chip, to create regions that can give that is now very hard to do. So I think to answer your question, that is the goal. We'd like to get to
I understand.
get the stage where we can do all those things, but right now it's not being done.
Yes, and just one last thing. When we test that, when we say that this particular biochip is correct or it is working fine, error free, what is the golden response that you take? It is the pathological test that is conducted, right?
So we need to have calibration done. So we need to have benchtop calibration so we know what is accepted range of outcomes. So we are measuring something, and the normal range is from A to B. A to B is calibrated for a test done on the bench. If you do it on the chip, the range may differ because the volumes are different. So we have to have a control experiment first, which tells us this is the normal calibrated range. And at the time we use a chip on a patient, we will then check if the outcome falls inside the range or outside the range. That's also one reason why it's so hard to do quantification. It's much easier to get the answer of yes or no. Is this present or absent? If it's in the range, it's absent. Outside the range, it's present, right? But if you want to say what is the concentration of this, then you have to do a lot more calibration to understand what you are measuring, the way it maps to what actually you're looking for. Because it's very hard to measure what you're looking for. Most of these are done indirectly. So you plot a graph. The x-axis, you basically are looking at what you measured, and the y-axis is what you're trying to measure. And you have a curve, which is called the calibration curve, that maps the x-axis results to the y-axis value. And this calibration curve has to be done in advance, experimentally. And that is a big challenge of these chips. On the benchtop, it's much easier to do because the volumes are larger. On the chip, because they've got very small volumes, even a 10% variation can make the curve shift a lot.
Yes, and you also said that these chips will be used for maybe 1 or 2 tests. So, the question that Shushmita ma'am raised is very vital, that we need a lot of such chips to do tests.
Yes, absolutely. But if you have very low cost, if you can just throw away, yes, you can. But then you have to make sure that they can be disposed of well.
Yes, yes.
Okay.
Any other questions? Okay, if there is no other question, I would request our head of the department, Professor Shaukat Maiti, to come and present this to Professor Chakrabarti.
Thank you so much, Dr. Datta. Am I audible?
Yes, you are.
Yeah, thank you so much, Professor Chakrabarti. It was really a overwhelming journey of this microfluidic. I can remember the movie Matrix, where exactly the microfluidics applications along with the agents. And I'm really this session is really mesmerizing. Thank you so much for giving us this sort of session for us and conducting this sort of session for us. A token of love, appreciation, as well as regards from the School of Engineering to you. Please accept this, sir. It's a great honor for us to be with you. So please accept this memento along with a digital. This is a digital e-memento for you. I hope in future, definitely we are getting in touch with you. Our students, our faculty members will be getting in touch with you in future. And obviously, the captain of the ship, our Professor Indranil Sengupta sir, without whom this cannot be done. So thank you so much, sir, for giving us this sort of
Krish will be with
enlightenment.
us. Krish will be with us.
Thank you so much. Thank you.
Thank you.
So it is really a pleasure for us. Thank you, sir.
Thanks
Thank you
a
so
lot.
much. It's over to Dr. Datta, please.
Thank you so much, sir, for this wonderful talk. I never thought that you will agree to give a talk with such a short notice, but it was Professor Sengupta. He said that no, write to him, he will. So
well,
I was
if Indranil Das asked me to do it, I will do it. So I cannot to him. I cannot
yes,
say.
sir.
Thank you.
Thank you, sir. Thank you so much.
Thank you.
Thank you for this.
Bye. Bye.
Bye, sir. So, dear participants, now I would like to tell you that please continue with your